Welcome to ICTP-SAIFR. I'm really happy to have you all here. We are really excited to organize this conference. If you need anything during the school, this is my phone number. My name is Pablo. Also, I'm putting the number of Emmanuel, one of the participants who is always here at ICTP for many of the schools, and he knows the city very well, so he created this WhatsApp group to coordinate with you guys going out from the hotel to places to dinner, to the bar, and so on, okay? So I'd like to thank the co-organizers, Rodrigo Soto, Danilo Liarte, Francisca Guzman Lastra, and also Leonardo Brunet for accepting to participate with me in this adventure of organizing this event. Also, the staff here at ICTP, which were really kind to help us organize everything. And, well, without further ado, now I would like to introduce Professor Julia Yeomans from the University of Oxford. She's going to tell us in the first lecture of her course about active nematics and mechanobiology. And thank you very much, Julia, and all the lecturers. Please, the floor is yours.
Thanks, Pablo. Thank you. Very nice to be here. It's always nice to visit Brazil. What would be absolutely fantastic is if you could ask questions. It's always much more fun lecturing when people ask questions. So please, please do stick your hands up and ask lots and lots of questions. Anytime, I'm very, very happy to be interrupted. Don't worry, this is not the first lecture, this is all of them. We're going to end up at a research level. I'm going to start today with background. I'm going to tell you about nematics, and then just a little bit about low Reynolds number hydrodynamics, because I think Rodrigo's going to talk about that as well. And that's to set the scene for talking about active systems and active nematics. But knowing about nematics is something everyone ought to know about when they're doing soft matter physics anyway, so hopefully it will be useful beyond just the rest of these lectures. And then I'm going to talk about active nematics and try to explain to you why these things show active turbulence and why they show motile topological defects. And then gradually moving on from there, I'm going to move to some of the more specialized bits of active nematics and end up trying to talk about how we can use these ideas in mechanobiology. So by the end, we really are at the research frontier, and the things I'm going to talk about at the end are things which I certainly don't understand properly, and I don't think anybody else does either. But you can tell me if you think I'm wrong. So it's very much starting from the beginning and ending up at what I think is a very exciting research frontier. So, liquid crystals. So I'm going to start talking about liquid crystals, and in particular, nematic liquid crystals. And this is the outline of this first part of today's lecture. We probably won't get much further than this today. So the first I'm going to start just by telling you what a liquid crystal is, and these things form lots of phases. We're going to concentrate on nematics, but I'll just show you the rest of them. And then I'll talk about order parameters and the Landau expansion, how we can write down the free energy of these systems, how we can describe their equilibrium properties. And then one of the very important things for the active systems is topological defects. So topological defects are going to be a big deal. I'll explain what they are. And then I will write down, I won't derive, but I will write down and explain the continuum equations of motion for liquid crystals, because we're going to have to understand the hydrodynamics of active nematics, and that's very much the hydrodynamics of nematics plus one extra term. And one of the questions you might think about as I'm going through this is, why on earth is she telling us about liquid crystals? Why are we starting with nematic liquid crystals? Why are these active systems called active nematics? And the answer is going to be symmetry. It's grounds of symmetry, and the equations of motion look very similar in both cases. So really the link is more in the mathematics than in the experimental systems. So I'm going to do some of this today on slides and some of it on the blackboard, and I'm going to jump between the two. So if I forget to put the lights on, just yell at me, okay? And let me stress again, questions are great. I'm a theoretical physicist, but let's just remember that liquid crystals are real. So the things I'm going to be talking about is molecules like that one on the left, which are long, thin molecules. The whole point of a nematic is you get this nematic behavior in systems which have a preferred axis, often things which are long and thin, and they can either be molecules or they can be colloids. The sort of length scale of these viruses is maybe 10 to 100 microns. So what sort of phases can you get in these liquid crystals? Well, I've drawn them as rods because it's a long, thin molecules that we're thinking about. These molecules have a special sort of symmetry. They have a preferred axis, and they pretty obviously do, right? These long, thin things have a preferred axis. But the important thing about a nematic, about nematic symmetry, is that they don't have a direction. We've got this axis, but that end of it and that end of it are the same. So it's not like something which an arrow on, which you'd expect for a magnet. These things have a special axis, but up and down are identified with each other. At high temperatures, this first picture here, these things form a normal sort of liquid. Okay, so they're random, pretty random. If you cool them down, or if you add extra molecules so that the concentration is larger, what they do is order in this phase here, which is called a nematic phase. So the word nematic is used both to describe this phase and also to describe the up-down symmetry of these molecules. A nematic phase has long-range orientational order. That means that if I look at this one here, then a very long way away, strictly if it's long range, an infinite distance away, it's more likely to be pointing in the same direction. So you have long-range orientational order, but no long-range positional order. The centers of these molecules are at random positions. This is the nematic phase, and really the only one I'm going to talk about. But these liquid crystals do all sorts of other things as well. For example, they can order in layers, where you now have some positional order because the center of molecules are in well-defined layers, but within a layer, there's no ordering. That's called a smectic A. You can have these cholesteric phases. A cholesteric phase means that in layers, you get this nematic ordering. So within a given layer, things are all pointing more or less in the same direction. But then as you move along one axis, that layer turns from place to place. Anyone know what we use cholesterics for? Yeah, do you want to shout out? I have to shout loudly so I can. Oh gosh, that's a bit technical. Probably, yes. Certainly for a nematic. A nematic, it's LCDs, and you do dope them a bit with chiral molecules. Okay, you know those color-changing ducks you get in the bath? Okay? You put them in the bath, and when they get hot, they change color. That's cholesteric liquid crystals, because the wavelength of this ordering changes with temperature. And the thermometers you put on your heads as well, the ones that change with temperature, again, that's cholesteric liquid crystals. Okay, and then of course eventually you can get a crystal. These molecules will form a crystal, and by that I mean something which has long-range orientational order and also long-range positional order. But this is the one we care about, the nematic phase, orientational order, but no positional order. So those are the sort of questions we might worry about with a nematic phase. I've said when it orders as you lower the temperature. That sort of makes a bit of sense, doesn't it? Because everything orders at lower temperature because the entropic contribution becomes less important. Also, it can order when you increase the concentration. As you push these molecules closer together, they'd prefer to align with each other. And that's because of it trying to minimize its free energy. And it's actually quite subtle. It's usually a subtle energy entropy balance in these systems, which gives you the particular phase. I've talked about nematic symmetry, and nematic symmetry is important. We have these headless vectors, a preferred direction, but up and down are the same as each other, and that's what makes these nematic phases special. And if we have an ordered phase, we need an order parameter to talk about them. And there are actually two different order parameters people use for these nematic phases. The first is called the director field, and that's just a vector in the direction of the molecules. So it tells me about the direction, and it's not a real vector, it's a headless vector. Up and down are the same as each other. That tells me about the direction of the ordering, but it doesn't tell me everything, because it doesn't tell me about how ordered they are. So you'd really like to know more than just the direction. You'd like to know how ordered these things are. And to do that, you actually need a more complicated order parameter. This order parameter is called Q, and Q is a tensor. It's a tensor, and we're going to worry about what that Q looks like now. So I'm going to do this one on the blackboard. So, ooh, fancy chalk. Right. So Q is defined like this. The order parameter Q is defined like this, Q alpha beta, okay? And I'm going to write it down in 3 dimensions, 3/2 average. I'll tell you what U is in a minute. U alpha, U beta, minus 1/3, delta alpha beta, where U is the unit vector along one of the particles, along the ith particle. So let's put an I label on it to show that it's along the ith particle. I'm defining Q like this. This is this unit vector, U, all right? Alpha and beta, I'm using index notation for directions. So alpha and beta are X, Y, Z in 3 dimensions. Okay, is anyone not used to index notation? The average, no. And that's a good question. Thank you. Questions are great. Coming to that next. That's the next thing. Okay, this average, the average is over particles, but it's an order parameter, so it changes from place to place. And so you take the average over a local number of particles, and then it can change to the next lot of particles. So you need enough that you're averaging over fluctuations, but it's not over the whole space. It's over a localized bit of space. Hello.
Yeah, The unit vector is, because the particles are apolar, then is the velocity vector, or what is it?
It's just a vector. This is just a single one of these particles, yeah? And that u is just a unit vector in its direction, okay? So this is averaging over, this would be, for example, the xx component of q would be ux squared minus a third delta xx, which is 1. Okay, this thing here is the delta function. It's 1 if alpha equals beta, and it's 0 otherwise. Hopefully that will become clearer as we actually work it out for something. I've written this down in 3 dimensions, okay? More generally, in d dimensions, that thing comes out as d over d minus 1. Works in 3, thank goodness for that. Okay, this in general is 1 over d. Okay, so now let's look at the properties of this Q-tensor. Sorry, did you have a question?
Maybe it's a bit dumb, the question, but you're writing, for example, the U has like a line under. Is it notation for vectors that are headless, or is it just a vector
This
notation?
is just a normal vector.
Ah, okay.
This one is, yeah. That's okay. That's a very sensible question. And questions are never dumb because, please, it's great when people ask questions. All right? Okay, so let's look at the properties of this Q-tensor. Let's just think about it, what the various properties are. Well, first of all, it's symmetric. A tensor is going to be symmetric if it's the same when I interchange alpha and beta, okay? Qxy and Qyx are the same. That's what I mean by symmetric. Is that right? Yeah, because if I switch alpha and beta here, I'm going to end up with exactly the same formula. So just from the definition, that is right. The second thing is that the trace of it is equal to 0. The reason the trace is equal to 0 is because u is a unit vector Okay, let's just check that. The trace means I'm summing the diagonal elements. So what I mean is qxx plus qyy plus qzz. Qxx is ux squared minus a third, because this is 1 if alpha and beta are the same. Qyy is uy squared minus a third. And so on. But ux squared plus uy squared plus uz squared is 1, minus a third 3 times is 0. So the trace is 0, okay? Because this thing has 0 trace. So let's just think how many independent components it's got. Anyone want to have a go at that? How many independent components do I have in this Q? (3D), how many? Yeah, go on, tell me. No, not 3. I'll go for 5, yeah? I'll go for 5. I reckon it's 5. Hopefully I've got that right, okay? Because if I have this 3 by 3 matrix, if I fix those 6, which is certainly the first try, those are fixed immediately because it's a symmetric matrix. But the trace is fixed. So once I've got those 2, that one's fixed because the trace has to be 0. So I'll do 5 in 2 dimensions. How many in 2 dimensions? 2. 2, so this one's in 3D, and 2 in 2D. This thing is carefully organized so that in the isotropic phase, where you don't have any ordering, it's equal to 0. Ooh, I'm going to have to walk a long way with these boards, aren't I? So in the isotropic phase, at high temperatures, Q alpha beta is equal to 0. Okay. And that sort of makes sense. That's what we want from an order parameter, yeah? What we want from an order parameter, it's 0 when you don't have any order. So let's just check that. Qxy, say, yep, is going to be ux, uy. If everything's disordered, what's the average of ux, uy going to be? 0. That's okay, isn't it? And then that's 0 because it's a delta function. Qxx, going to have ux squared. But then what's ux squared? Well, we know that ux squared plus uy squared plus uz squared is 1. We're in the isotropic phase, so each of them has to be a third. So that's a third minus a third delta alpha beta, right? And that's going to be a third minus a third, so that all works. All right? And then the other thing we want to know about is when this thing is in the ordered phase. So I think the easiest way to see what's going on is let's look at a perfectly aligned phase, and let's have it perfectly aligned along Z. And let's work out what Q is equal to. Well, let me write it down, and then we can just check it. It's going to look like this in the basis where my rows and columns are labeled by the axes X, Y, and Z. Okay. Is that right? This one here is minus a half, so QXX is minus a half. QXX, right. I'm in the ordered phase, so everything is like this along Z, perfectly ordered. So this is the Z-axis, yeah. So we've got to work out what QXX is. Well, what's UX squared in that phase? Zero, yep. Because I know x components, good. Then I've got minus a third, delta xx is 1, because alpha and beta are the same. So I've got 3 halves times minus a third, which gives me my minus a half that I've got there. QYY is obviously the same by symmetry. QZZ, does this work? It's going to be 3 halves into UZ squared. UZ squared is going to be 1, yeah, from all this, minus a third, which is 1. So that works. And more generally, you can check it for any system that you like. The largest eigenvalue gives the magnitude of the order. How many are aligned along Z in this case, how much the alignment is, and the largest eigenvector gives the direction of the order. Okay, so the largest eigenvalue gives the magnitude of the order, and the largest eigenvector gives the direction of the order. I haven't proved that, but I think well, if you don't like it, try some configurations and see. We have only thought about a particular sort of ordering. We've only thought about uniaxial order, where it's ordered along Z, yeah? Or along a direction which we've chosen to be Z. This tensor is a bit of overkill for ordering like that, because really you only need the direction and how many are along there. The reason people use it is that it can also talk about a secondary sort of ordering in the plane perpendicular to the Z-axis. For example, you could have most of the nematogens, most of the liquid crystal molecules pointing in this direction, and the ones that aren't can be isotropically ordered with the components in this direction can be isotropically ordered. But you could imagine one which actually, if it's not pointing this way, wants to point that way rather than there. So you get preference along the x-axis compared to the y-axis. That's called biaxial ordering. And you can do it with this Q-tensor. We're not going to worry about that. But one of the big deals in liquid crystal physics at the moment is whether you can actually find real systems which have this biaxial ordering. I've got a cute example here, which I'm not going to do on the board, but which you can do in the problem set tomorrow, just to play with this a bit. Right, any questions? Okay. So that's, whoops, sorry. If you must use up all my blackboard, you deserve that. 818? Yep. So if you're thinking about magnets, all right, and you want a simple theory of ordering in a magnet, what's the simplest theory you can use? Let's see if you know about this. Anybody like to tell me? Sorry? Well, the Ising model would certainly work if it's... I'm after Landau theory, yeah? Have you heard of Landau theory? Where you take your free energy and you expand it in terms of an order parameter. Anyone not familiar with Landau theory? Okay. So what I'm going to do is write down the equivalent of Landau theory, but for these liquid crystals. And in fact, you sort of need to know it exists, but it's not very, very important for what we're going to talk about later. And I'll explain a little bit why not. So what we're worrying about now is to find a position for the transition between what's happening at high temperatures and then if I lower the temperature, using a Landau-like approach. And if you're doing liquid crystals, it's called the Landau-de Gennes free energy. Okay, and what I do is I write down an expression for the bulk free energy as an expansion in the order parameter. So the bulk free energy is going to be some constant term, which doesn't do much normally. And then a term in Q squared, put a minus sign, doesn't really matter. A term in Q cubed, and a term Q beta alpha, Q gamma delta, Q, delta, gamma, plus higher order terms. I claim that those are the only possible terms that you can have to fourth order in Q, independent terms. This free energy is a scalar. So I have to make sure that all my indices come in pairs. All right, remember when it's in pairs, I'm using a repeated index notation. So I put alpha is x, and alpha equals y, and alpha equals z, and add them all up. Right, that's standard way you play with these indices. And so you will also have to have all the indices in pairs so that you end up with a scalar, so that your free energy is a scalar, which is what you need. I haven't got a Q term, a term just in Q there. You might think I need a term in Q alpha alpha. Why don't I have to bother with that? It's traceless. Yeah, remember Q is traceless. That's the trace of Q. And so this term's 0. Good, well done. And then the other thing you might worry about is whether I can have a term which looks like Q alpha beta, Q beta gamma, Q gamma delta, Q delta alpha. And I was worrying about that last night, okay? But it's okay, because if you try and see what that's going to give you, you actually get something proportional to that. I just did it by using a Q-tensor which looked like this. Remember, it was one like this. Okay, and if you bung that in, those terms aren't identical, but they're proportional to each other, so it just renormalizes, changes C. Note, because we've had a lot of trouble with this, but it's ever so easy, really. In 2D, you can't have this term. Okay? And the reason is, if you write down Q in 2D, right, it has to be symmetric, it has to be traceless, and I've written it down in whatever basis it comes out as diagonal. And then if you work this out, you'll find it's 0, basically because the trace is 0. So in 2D, you don't have this term here. In 2D, this expansion looks a bit different. Okay, so now let's put this formula in for Q. What I'm assuming in writing down Q like that, like this, is that the thing is uniaxial. I can always take my symmetric matrix and diagonalize it. Okay, so I've done that. I've chosen a coordinate system in which my Q-tensor is diagonal. It's got to be traceless, so one of these is fixed. Also, the fact that I've chosen the x and y component the same means I've just using uniaxial order, I'm assuming no preferential ordering in the x and y direction. So that is actually the most general form of this Q-tensor. For uniaxial ordering, okay, and along whichever axis, which I've chosen here to be the z-axis. So I can take that and put it in here. That's easy enough to do, right? I just write down this q squared, qxx squared, plus qxy, qyx squared, plus, I think there are going to be 9 terms altogether when alpha runs through x, y, z, and beta runs through x, y, z. And what you find is that that particular term, you can check it for yourself, fact, it's not that hard because the off-diagonal terms are 0, so you just get diagonal terms coming in. And you end up with 3aq squared over 2. And you can do the same thing for these other terms. And if you do that, you can write down the free energy in a much more easy way. FB is F0 plus 3 over 2 aq squared minus some b times 2 cubed plus some c times q to the 4th. So what I've ended up with is just really a simpler way of writing down the Landau expansion in terms of q, which is just the magnitude of my order. Okay? This works for uniaxial system. This one is more general. So looking at that, we want to understand which phase minimizes the free energy. Easiest way to do that is to draw what these curves look like. I can't do that in my head, but I can easily go away and plot it on Mathematica or something or work it out. And it looks like this. That's Q, that's the magnitude of the order, and this is FB minus F0. For small q, it's going to look quadratic. For large q, it's going to tend off to infinity. This is going to make it do something fancy in the middle. And what you find is you can either have a curve which is that shape, but if you decrease A, what you end up with is a curve which starts to look like this. And then it goes like that. And then it goes like that. So I identify this as decreasing the temperature, all right, just because then it gives the right physics. And then I say, what's the minimum? Well, here, Q is equal to 0. That's the isotropic state. If I come down in temperature, this is still the minimum, but I'm developing a state there, which is another minimum, but not the global minimum. So this one here is a metastable state. All right? And then that moves down till it hits the axis. So now I have two coexisting states, and then this one wins. Yep. So that becomes the equilibrium state. So what's it called when you get a jump like this in the order parameter? The order parameter's there, and then it jumps to this value there. First order transition, Q jumps, right? And what you get is a weakly first order transition. All right. Why she said weakly, the answer is that we sort of know that from experiment. You can't tell it from this, because obviously it depends on these values of this A, B, and C. And the first order transition happens at B twiddle squared over 6C twiddle, and at a value Q, which is B twiddle over 2C twiddle. So this value of Q here is what I call Qn. It's actually really easy to find that, if you think about it a bit, right? What you need to find is that this is a point where FB minus F0 is 0, that point there. And it's also a special point because it's a minimum, so you actually get a repeated root of FB minus F0 is equal to 0. So this is the point where FB minus F0 has a repeated root. So you might like to check for yourselves that I've done it right, and this is where that repeated root is. Yeah?
I see also that the value of Q for the minimum is changing towards larger Qs. Is that just because of the drawing, or should it be in the same value of Q?
It's meant to be moving to larger
right?
Qs, yeah. Yeah. That is right. But it's not obvious without actually sort of doing it. Other questions? There's a bit of a question mark here, isn't there, though, because a Landau expansion is for a small value of the order parameter, yeah? And so I've got this order parameter jumping from 0 to a value which actually in real systems is small, but it's definitely a first-order transition. So you might well wonder, you know, why is this Landau expansion working in the system? And I think no one really knows the answer to that, but it does. It works extremely well. You have to fix A and B and C from experiments, but if you do that, this Landau theory works absolutely brilliantly for passive liquid crystals. And I think that's just luck rather than anything else, okay? And if people are worrying, real people doing real device physics, it's actually useful, are looking at liquid crystals. This is a theory which is pretty much universally used to understand where that transition is. Right, so has anyone got any questions? Now, having talked about the bulk free energy, now we have to worry about changes in this system, right? Sorry, not changes. What happens when the order parameter changes from place to place? Right, distortions in the ordering. This tells me about the magnitude of the order, but in fact, in these systems, the magnitude of the order is often not very important. What matters much more is the fact that the direction of the ordering can change from place to place. So now we need contributions to the free energy which depend on derivatives. Let's see, I think I've got yeah. Okay. Oh, I've written elastic liquid, just to remind you, these are liquids. These liquid crystals really are liquids. If you look at them in a test tube, they slosh around. But they're elastic liquids. What they want is for the ordering to be nematic. So if you muck it up, right, in some way, you're going to get an extra energy. And you need to include that energy in your Landau expansion. So this is a very nice picture, which I've always liked, taken from a Dijen book, the famous Dijen book on liquid crystals. And what you can see are the 3 different sorts of distortion you can get in these systems in 3 dimensions. You can have a splay distortion, which basically, if you take your surfaces and do that, and they're still stuck to the surfaces, they're going to be miserable because they have to splay out away from their natural order. You can have these things bending, so they're ordered like that, and then they bend around like this. In 2D, that's all you can have, but in 3D, you can have them twisting. So if you twist the one up here, the direction of these things has to twist from one side to the other. And, okay, so this is section 4. This is the elastic contribution to the free energy and the famous Frank elastic constants. All right. And now I'm going to write this in terms of the director field, not Q. Okay, my director field N. N is a headless vector, and it tells me about the local direction of these things. So if these are my molecules, and then they suddenly do that, I have now this director order parameter, which tells me about the direction, but not the magnitude. It would look like this, and then by there it would have gone to that. So we are jumping here. We're jumping to using n as an order parameter, and I'll tell you why at the end. But that's fine. At the moment, what we care about is we're assuming this thing is fully ordered, so my Q is equal to 1. That's fully ordered locally. All that can change is the direction. So let me write down FD, which is the distortion-free energy, and the K1, K2, K3 are elastic constants. K3 over 2 n vec curl n squared. I'm looking at distortions in the free energy. I'm looking at changes in the direction from place to place. So I have derivatives. I'm looking at, I've got to have that direction and that direction the same. From the physics, if things twist in that direction or twist in that direction, the energy has to be the same. So I have each of these terms is a squared term. You can then argue for a long time whether there ought to be extra terms in there, and people did, but it turns out that these, if I have a system without a surface, these are the only possible distinct terms that can contribute to second-order derivatives to the free energy. So they're the leading term to second-order derivatives. They're the only possible leading terms, and they fit the pictures up there. This one is splay, I think, isn't it? Splay, div changes splay. Yep, this one is splay. This one is twist, that one. What's it? Oh, wrong way around in my notes here. And that one is bend. Splay, twist, and bend. They're the distortions that are drawn on the slide above. Because we're theorists, we don't actually care too much about numbers. We almost always use the one elastic constant approximation. And if you do that, the distortion-free energy is a bit easier. It comes out as div n squared plus curl n squared. Yeah, so this is a dot product, and that's a vector product. You have to think about which direction your distortion is. Yeah. We'll play. Sorry, other questions? I've got one more thing to say, and then we'll have a short break and a short problem. Anything? Other questions? Right. I've jumped to n here, right? But, I could have written down this distortion-free energy in terms of my order parameter Q. They're just different ways of representing the same physics. If I write down the possible terms to second order in Q, I need derivatives, right? The distortion-free energy comes out as L1 over 2 d alpha Q beta gamma squared plus L2 over 2 d beta Q alpha beta squared. Those are the only two independent terms to second order in Q. And that takes a bit of getting your head round when you first see it, right? Because if I write down my Landau free energy here, I have 3 parameters to describe what's going on. If I write it down here to second order in derivatives, there are only 2 independent parameters. And then if you include the third order, I think it's 9 possibilities. And so there is not a one-to-one correspondence. Just because Landau theory looks like that here, you don't necessarily have the same number of terms here. All right? And that's a bit strange, but that's right, and that's how it works. And if you really want to match the 2, you need to choose one of your 9 different third-order terms to include here. Now, we're going to have a short break come problem-solving thing. So let me just set up the problem, and then you can have a go at it. This is to worry now about surfaces in these liquid crystals. Surfaces. All right? And liquid crystals, here are my surfaces, and you can make the liquid crystals lie like this along a surface, or you can make them lie perpendicular to a surface. This one's called homogeneous anchoring. And this one's called homeotropic or normal anchoring. And if you're setting up display devices like your laptop screen, this is super important, these different sorts of anchoring. The way they do it, this is amazing actually, this one here, to get them to stick like that, you take the surface and a duster and you do this with it. This is very technical experimental physics. Okay, this one you bung in a surfactant. We don't worry too much about that. But you know, how do I do this problem? Where can I space for my problem? I've got a surface here at y equals 0, all right? And I have strong homogeneous anchoring, so in-plane anchoring there. The other one over here, I'll put at y equals L, so this is my coordinate y. And here I'll have strong in-plane anchoring along, what have I done? A different direction. Sorry, so this one is along Z, and this one is along X. So I fix the liquid crystals here along Z, I fix those along X, and I want to know how the director changes between here and here. And the reason I want to know is this is a very simple problem using the Frank free energy, and it's a really good problem to practice to understand what's going on. So let's stop now till 10 past, which is a small break, which you can either have a nice break, there'll be coffee later, you have to come back at 10 past to carry on with this, right? All right, and you might just think how to do that problem, and I will write the beginnings of the answer on the board. So if you'd like to have a go at that, or you'd like to have a little break, I'll start talking again at 10 past. Okay.
Thank you, Julia. So in 10 minutes, we are back.
Okay. So this clock is 2 minutes wrong, but I think we'll go by this clock on the basis that it might be easiest. So if anyone's got any questions about that, happy to talk to you at the end. Hopefully that's helpful there. We're going to be using the same ideas now. And that's to look at defects in this system. So now we're looking at excitations around the ground state. If you just have something like this, which is a localized bend distortion, it really doesn't matter much, because those red molecules or nematogens or colloids are just going to relax back very easily to the proper ground state. That's just going to be a minor fluctuation. But in these systems, you can have much more persistent defects, much more important defects, which really affect the physics. And these are topological defects. Okay, so in 2 dimensions, these are the main topological defects. What I'm plotting here is the director field. That red one is a +1/2 defect for reasons which I will talk about. We'll understand why it's called +1/2 in a minute. That one there, the 3-fold symmetry, is a -1/2 defect. And what I mean by topological defect is one which can't be undone without changing the director field all the way out to infinity. It's like a knot. In a closed piece of string, you can't undo it. So these things on their own have an infinite energy because they distort the director field everywhere. So they can only exist in a finite system or in pairs. If you have a plus and minus pair, then a long way away, the director field will not be distorted. These topological defects are all over the place. These are just some examples. And so it's not just liquid crystals, but liquid crystals have been a great testing ground for looking at topological defects because the maths is rather simpler in these systems than in many other systems. And what this is a movie which shows topological defects being formed as you quench a liquid crystal. What I mean by quench is that I start at high temperatures with a completely random orientation of nematogens. I then very quickly lower the temperature into the nematic phase. What happens very quickly is that you get nematic domains forming, but then there's a mismatch between the domains, and the mismatch between the domains are the places where these topological defects are formed. And then much more slowly, the topological defects gradually move towards each other and anneal out. Plus and minus pairs move towards each other and anneal out. So here's a picture. There the domains have formed. Those blue dots are the topological defects. They move towards each other. The sort of white bits are the domain boundaries. And they gradually anneal out. Let me just play that again. So you really get 2 time scales in this system. First of all, you get local nematic order, but their domain boundaries where it's gone wrong, because this will grow like that, and that will grow like that. And then the defects anneal out. Okay, so what I want to do is the mathematics of these topological defects, just the simple form of the maths. I'm doing the maths in 3 dimensions, but I'm always going to have translational symmetry along Z. So what I'm going to say works, probably is most useful, in fact, in 2 dimensions. So we'll use it later on in 2D. And I'm going to draw these various sorts of dislocations, topological defects. And then I'm going to label them, and then I'm going to say where the labels come from. Let's try strange. Ah, white chalk. Yeah. Okay. So this is this plus a half one. What I'm drawing here is the director field, the direction of the director field, so each of the little nematogens, each of the little molecules are like that. That one is m is a half, and phi 0 is 0. Oops, I have to do it way around. I've got here, I'm going to get in a mess. This one here is the minus a half defect. M is minus a half, phi 0 is 0. This one here, if you have one's looking like a star, that's an M is 1 defect. Phi 0 is 0. And you can also have an M equals 1, which looks like this, where the nematogens go round in a circle. This one is M is 1, and phi 0 is pi by 2. Yeah? I haven't told you yet. Yeah. And indeed, I haven't really told you, if you haven't seen it before, what this M is either. Coming to that. Coming to that. Okay? So let's just get this straight. The lines are the directions of the director, direction of N, just so you know what I'm drawing. In places like this, okay, this is called the core of the defect, the middle of the defect, and you can see in the core of the defect, these molecules are in a complete mess because they don't know which direction to point, okay? And what happens is that in the defect core, Q, the strength of the order parameter goes to 0. Essentially, the thing melts because it's so confused about which direction to go. And it turns out that the order is biaxial in the core, but don't worry about that. And actually, that's why when you're doing simulations, using Q as the order parameter and not N is brilliant when you're looking at these topological defects, because it allows the magnitude of the order to change. And so topological defects come out automatically from the simulations. Whereas if you use N, you're in a bit of a mess because N isn't able to allow Q goes to 0 because the director order parameter always has a constant value of Q. So that's one of the really really good reasons for using Q as your order parameter. The other thing we have to worry about is just sort of bookkeeping. Theta is the director angle, all right? The angle the molecules point relative to some axis, which is this axis, I think. Phi is the polar angle. So it's the angle in my coordinate system. So in general, theta will be a function of phi. Phi tells me that I'm moving around here, and then the value of theta changes as I move around there. So I want to work out the director field. And what I'm going to do, the mathematics is almost the same as what you've just been doing, those of you that have been keen. Okay. I am thinking about a system which is translationally invariant along Z. So any Z derivative is 0. So basically, I'm in 2D. I will have a direction up here, but I'm forgetting about it. And so my director I can write as cos theta, sine theta, 0. I'm assuming that N is in the plane. I'm assuming that N is in the plane. I can forget about the z-axis. And I'm going to be in the one elastic constant approximation. So I can actually do the calculation. And in that approximation, FD, the distortion free energy, is a half K into div n plus curl n squared, sorry, div n squared plus curl n squared. And I want to integrate it over all space. So I better have an integral sign in there, hadn't I? That's adding up the distortion energy over all space. And if you add up div n squared plus curl n squared, you just have to do a bit of algebra, and you find out that's the same thing as grad theta squared, a half K, the integral of grad theta squared, and then I'm integrating over the plane. Sorry, I didn't say that quite right. Let's say that again. All right, this is my free energy in the one elastic constant approximation. If I work out div n and curl n, I can rewrite that in terms of theta, and it comes out as grad theta squared. I'm integrating over the plane, r d phi. Here's my polar angle. And then I'm integrating over z, but I don't bother about that because it's translationally invariant. OK, questions? That's just the calculation you've just done, but in slightly different coordinate system. I want to minimize the free energy. To do that, I use the Euler-Lagrange equations. All right. So you just have to look up how to do that if you're not used to it. And you end up with del squared theta is equal to 0. And I'm trying to minimize the free energy. So if the directive field depended on r, if it changed going outwards from the origin, it's pretty obvious that that's going to increase the free energy. So it would be sensible to look for a solution which just depends on phi. So we want a solution independent of r to minimize the elastic energy. All right, so if it's independent of r, I can rewrite that as just d2 theta by I would use that, but it's the wrong bit of board. Let's do that. d2 theta by d phi squared is equal to 0. All right, so that's just assuming theta just depends on phi and not on r. And if I integrate that, I end up with theta equals m phi plus phi 0, where m and phi 0 are constants. So what are the allowed values of m? Right, this is the extra bit of physics, which is nematic physics in here. If I change phi from 0 to 2 pi, I have to get back to the same value of theta. But does it have to be exactly the same value of theta? I'd be fine if theta changed from 0 to 2 pi, right? But what else could theta do? Go on then. I've got people waving their hands about. Someone be brave enough to tell me. Exactly, thank you. Yeah, well done. All right. I want to go all the way around and come back. If I come back to here, I need to have the same director as where I started. Yeah? But these directors are the same if they look like that or like that. And so phi has to change by pi or 2 pi or 3 pi or 4 pi. So if phi varies from 0 to 2 pi, from here, theta varies from 0 to 2m pi. Yep. And that's okay if m is an integer, obviously, but also if m is a half integer. Because it's all right if it goes halfway round, because it will look the same because of this head-tail symmetry. So that sorts m out. All right, the allowed values of m. Let's just check here, see if I can get this to work. I need a pencil with a thing on the end. That will do probably. You're allowed to do this for yourself, right? So I'm going all the way around. I'm going all the way around here. This changes, goes half a way around. So m is a half. Here I'm going all the way around with my director. This ends up pointing the same way, so m is 1. This one here, m is minus a half because I go round, but I actually turn the other way than I did there. You need a pencil and a drawing of these things and do it for yourself just to check that that works. So that sorts m. This phi 0 is really just an initial condition. Phi 0 tells me where I start at theta equals 0. At theta equals 0, my phi, my polar angle, is 0. At theta equals 0 here, again, my polar angle is 0. Doesn't matter here. Here, polar angle is 0 at theta equals 0 still. Here, at theta equals 0, my polar angle is pi by 2. And here it does make a difference for the m is 1 defects, and more generally you can end up with spiral type defects if you start off the thing like that. And that's fine, they're degenerate. The spiral defects are degenerate. That sorts phi 0, that's just an initial condition, doesn't matter for the half ones, all it does is rotate them in space. For these, it actually makes them look topologically, look different from each other. Yeah, one more thing I had to say, which was this phi here, this angle is just the polar angle, tan to the minus 1 y over x. And that's good, right? Because this is singular at the origin. And that's good because these defects you expect to have this singular core at the origin. Okay, questions? So now I just want to write down the free energy of one of these defects. That's easy enough to do. I just take this equation for theta, and I put it in this formula for the free energy, and I see what I get. So I need a space to do it. Let's do it over here. So I use my free energy. I'm just rewriting what I've got on the other board. Grad theta squared r dr d theta. This is very easy. Theta is m phi plus phi 0. So then I look up how to do grad in polars, and it's 1 over r d by d phi of this. So grad theta is m over r along phi dot, yeah?
Yeah. So we saw like 4 types of defects,
yep.
And 3 of them were kind of symmetric. So we thought like the dependency of R, that R doesn't matter because they are like isotropic. But the first one, the comet one, there's like a dependency in R, right? Or not?
No, it doesn't.
No?
If you think about one direction like this,
yeah.
Along there, they do actually have the same angle. Along an R direction,
Oh, okay.
it does have the same angle, whether my diagram, my drawing did or not. is not obvious, but it is okay. But it's a sensible question, yeah. Any change in R will increase the free energy. Good, other questions? Yeah. Where am I? So, okay, so this is grad theta. Remember that the grad is 1 over r d by d phi of the thing. So putting that in there, let's do it down here so I don't run out of space. Fd is a half k, the integral of m squared over r squared r dr times 2 pi for doing the phi integral. And so this is pi k m squared log. And then you're in a bit of a mess, aren't you? Because I've got log r, and r is divergent. R, if I make this 0 to infinity, which is what first thing you do, you're in a mess because the energy diverges. That's what I said, these things have infinite energy in an infinite system. So you have to cheat and put in a cutoff. You put the radius of the core down here, because this theory doesn't work near the core. It's assuming that the order parameter has a constant value and the order parameter goes to 0 near the core. The thing melts, so the whole theory using a director field goes wrong there. So it's sorting out a problem with the theory, not with the physics. And then here you have to have some sort of cutoff, R max, caused by the boundaries of the system or maybe by other defects. And then you can do this. It's just R max over whatever I called the cutoff. So this thing is cut off by walls or other defects. And this thing here is cut off by the core radius, which is of order the dimensions of the molecules or colloids. I'm not going to do it because of time, but what I would do next is look at the interactions between these defects. And what you'd find, as you might expect, is that plus and minus defects attract each other. They behave like charges, whereas 2 plus defects tend to repel each other. That's due to the elastic energy. If I have a plus and a minus, they'll gradually move together and annihilate. If I have 2 pluses, they will zoom off to infinity. Okay, so this is what we've done today. See where we're up to. Oh, sorry, I'm going the wrong way. That's what we're doing tomorrow. There we go. All right, so I'm going to write down the continuum equations of motion tomorrow, and then I'm going to talk a little bit about low Reynolds number hydrodynamics, and then we'll get started on active nematics. Okay, thanks.